Good morning to one and all, and my name is R. Joseph Paul, Assistant Professor, Department of Mathematics, SNS College of Engineering, Coimbatore. And today we are going to discuss about the quadratic form to canonical form by using orthogonal transformation. So when we convert a quadratic form to canonical form by using orthogonal property, we need to find an eigenvalue and eigenvector of a matrix. Then we have to normalize. Then we are finding the canonical form of the matrix by using orthogonal transformation, by using the orthogonal property. So this is a working procedure how we have to work for the quadratic form to canonical form. First, the quadratic form of the matrix, quadratic form to be converted into matrix form. Next, we are finding the characteristic equation, which we have already discussed in the previous class to find the eigenvalues and eigenvector. Next, we are finding the eigenvalues and eigenvector. Then we are finding the normalized model matrix N, and we are calculating its diagonal value by taking the formula N transpose of An. Then we are finding the canonical form. It is defined as CF Yn of, that is Y transpose of Ay. Then we are finding its nature of the quadratic form. Nature, we are saying we have five natures of a quadratic form: positive, negative, semi-positive, semi-negative, and indefinite nature. So when we say natures of the quadratic form is positive, we are saying based on the eigenvalue. If all the eigenvalues are positive, we are saying it's positive nature. If all the eigenvalues are negative, we are saying it as a negative. If one of the eigenvalues 0, the remaining are positive, we are saying it as a semi-positive. If one of the values 0 and the remaining are negative, we are saying it as a negative semi-nature. And if it is a combination of positive and negative, we are saying it as an indefinite nature. So this is the nature of the quadratic form, which is calculated, or which we are evaluating by using properties of the eigenvalue. So this is what we have discussed about its nature of the quadratic form. So here we are taking a problem to find the quadratic form 2x3 plus 3y square plus 2z square plus 2xy. We are converting that into a matrix 2 1 0 1 3 0 0 0 2. That is, we are taking the diagonal element as same, the remaining element is divided by half. So d1 is nothing but the first element, we are saying it is positive, and we are taking d2, that is the second 2 by 2 minor matrix, that is any possible 2 by 2 matrix in the A, and we defined it as first one, that is 2 1 1 3. We are taking it as 5, and d3 we are saying it as determinant of A, we are saying it as 10. So here we are saying all the three d values are positive, so we are saying it is positive defined. Now we are coming across with the quadratic form. So the problem is given as 6x square plus 3 times of 2x square, that is x2 of x square plus 3x3 square minus 4x1 x2 minus 2x2 x3 plus 4x3 x1, which we need to find the canonical form by using orthogonal reduction and its nature of the quadratic form. So first we know the quadratic form must be converted to matrix. So by taking its formula, we are converting the quadratic form to a matrix. Then already we discussed how to find the characteristic equation. So by taking its formula, because the matrix A is a 3 by 3 matrix, so we are saying lambda cube minus s1 lambda square plus s2 lambda minus s3 is equal to 0. S1, S2, S3, we know S1 is sum of the diagonal element. S2, we know it's a sum of the minor matrix of the diagonal element. S3 is determinant of A. So we are forming a characteristic equation in the form of lambda cube minus 12 lambda square plus 36 lambda minus 32 is equal to 0 after substituting the value of S1, S2 and S3. Now we need to find the roots of the eigenvalue. So here the roots are calculated and the root values are 2, 2 and 8. So we are saying the roots are repeated because 2 and 2 it's repeated twice. So we are saying the roots are repeated. So next we need to find the characteristic equation. Similarly, we are coming across by taking a minus lambda of x is equal to 0. So here the case 1, when we take lambda is equal to 8. So a vector can be calculated in any order, not only by taking the first case 2 comma 2 comma 8. It's your choice by taking by calculating the value of the eigenvalue, that is eigenvector, by taking any order of eigenvalue. So here 2 comma 2 comma 8 is an eigenvalue. So first I am taking where lambda is equal to 8. So same, I'm substituting the lambda value and I'll get a equations. I need to verify all the three equations are same, are different, or any two is same and one is different. So we are using the property and we are calculating the vector value. So we have arrayed x1, x2 and x3. So we are getting all the three eigenvectors by using the orthogonal property. Now we are going for normalized it. So I am normalizing the matrix x1, x2, x3. So we are normalizing it. Normalized matrix, we are finding its transpose of normalized matrix. Now we are converting into diagonal matrix. So we know diagonal is nothing but d n transpose of a n. So we are substituted. So when we finding the diagonal matrix, we will occur a diagonal matrix because we are calculating diagonal elements as d of n transpose of a n. We are calculating diagonal element. Diagonal element here is nothing but an eigenvalue will occur. For all the problems, when we calculate the diagonal matrix of a quadratic form to canonical, the diagonal element is going to be the eigenvalue of it. Now we are converting into canonical form by taking its formula y transpose of dy. So we will have a quadratic form. So here we are saying 8, 2, 2, all the three eigenvalues are positive. So its nature is going to be a positive nature. Similarly, we can find for so many problems for discussing the quadratic form to canonical form. Thank you.